to talk about what's real and what's not real, particularly when it comes to scientific data and how scientific data is presented and packaged to the public. Data that we see is often manipulated or processed, and this isn't for nefarious purposes. The data that we see is presented to us in such a way to enhance the scientific value as well as the aesthetic value. So it's not for nefarious purposes. Although sometimes we do see some interesting things. Not too long ago, a French physicist caused quite a stir for tweeting out a photo of a planet that turned out to be chorizo. Now, if the internet can't tell the difference between sausage and space rocks, how are we to know what's real, right? Especially when it comes to astronomical images, which contain objects that are so far removed from our everyday experience. Now, there's been a lot of excitement about the images released by the James Webb Space Telescope recently, and this is one of them. This is the Carina Nebula. The Carina Nebula is an enormous cloud of gas and dust. And inside this cloud of gas and dust, stars are being born. It looks a bit like a mountain range, but the tallest peaks are about 7 light years high. It's beautiful, it's stunning, it's a treasure trove of scientific information. But is it real? If you were to fly a spaceship alongside the Carina Nebula, would it look like this? And the answer is it wouldn't. The colors in this image are not real. It's false color. But just because it's false color doesn't mean that it's fake color, and it doesn't mean that this image is a fake image, right? And so we need to talk a little bit about the nature of light and the nature of color. We see color because of the interactions of light with matter, right? So for example, imagine a red rose on a sunny day. The petals of that rose look red because all the colors of the sun's light is being absorbed by that rose, except for the color red, which gets reflected back to us. And this is happening at the atomic and the molecular level. Electrons inside of atoms of different materials, they vibrate at different frequencies, allowing for this transmission and reflection of different colors of light. Now, how we perceive that light, how we interpret that light, a lot of that is learned based on our experiences of light. So if I were to ask you what these 3 colors remind you of, most people pretty quickly would say, yeah, this looks like a traffic light, right? And someone had to decide the colors for this very familiar scheme. And in fact, this scheme dates back to the 1800s in the railroad industry. So they decided that red would be stop because the association of the color red with danger. But originally they chose white for go and green for caution. The white for go caused some problems. There's an incident in 1914 where the red lens fell off, leaving behind a white light, and a train plowed through a stop signal, colliding with another train. After that, they decided to use green for go and then yellow for caution. Now, what if I were to show you another set of colors? If I were to tell you that that top row had something to do with weather, you'd know right away, right, that red color, if you're seeing that around your neighborhood, it's going to be a messy commute. If I told you the middle and the bottom had to do with snow or ice, and you saw that dark blue, you saw that dark purple, you might want to check to see that the college is open before you drive over here. Now, how we interpret colors is learned, right? The point is we're conditioned to seeing colors in a certain way, whether it's a stoplight or a weather map or traffic levels, right? And this is true for astronomy as well. We have been conditioned by the Hubble Space Telescope color palette. We're very used to the Hubble images, right, and that color scheme. And the astronomers who are working on the James Webb images today know that. So the choices that are made today in the color schemes are rooted in decisions that were made way back in the 1980s. Because it would be a little bit disconcerting if the colors of the universe completely changed just because we got a new telescope, right? All right, so we're going to talk a little bit about what light is. And in my astronomy class, I spend a lot of time talking about light. And this is because to an astronomer, light is everything, right? are unique as a science. Astronomers can't plan their experiments the way other scientists do, right? We can't take the star into the lab, slice it open, look at it. We can't dissect our galaxies in the classroom. All we know about the universe comes from an analysis of the light that reaches us. It's amazing when you think about it. Now, if you've ever thought about what light is, right, you're not alone. Scientists and philosophers for centuries have wondered about the nature of light. Now, we know today that light behaves as both a particle and a wave, depending on how you measure that light, right? But today, for our purpose, we're going to think about the wave nature of light and discuss how that wave nature creates colors, right? Now, our little human eyes are sensitive to the color red all the way out to the color purple. And colors happen because the colors of light are different wavelengths and different energies. So red light has a long wavelength and a low energy, and purple light has a shorter wavelength and a higher energy. But there's more to light than what we can see with our eyes, right? So if we look at the higher energy end of light, beyond the purple light, we get ultraviolet, X-rays, gamma rays. If we go on the lower energy side, longer wavelengths than red light, we've got infrared, which is heat, we've got microwaves, and we've got radio waves. And radio waves are light as well. But I want to take us back to visual light for a second. And I want to remind you that blue light has a higher energy than red light. So once you know this, you will be as frustrated as I am every time you use a faucet, right? You may have noticed this is how faucets are usually colored. This is a photo I took in one of the restrooms in the Science Center on our Rockville campus. But this is pretty common, where the hot water is colored red and the cold water is colored blue. To astronomer, this is completely wrong. Blue light is hotter than red light. Now, astronomers look at all colors, from the invisible to the visible, and our instrumentation is sensitive to different wavelengths. The James Webb Space Telescope sees from visible orange to the middle of the infrared. Now remember, that infrared light is invisible to our eyes. Whenever astronomers are creating images from light outside of the visible region, they have to use false color, right? So they're assigning that invisible light a visible color, and they're making decisions about what that color is, right? So let's talk a bit about false color and how astronomers create colorful images that you see. Astronomers use filters to create color in their images. And these filters are essentially colored pieces of glass. Like, imagine a piece of blue glass, right? A piece of blue glass is going to let blue light pass through it and nothing else. A piece of yellow glass is going to let through yellow light and nothing else. So what astronomers do is they measure the intensity of light through these various filters, combine it to make a colored image. The same is true for invisible light. So astronomers will use filters that block everything except little narrow bands of, say, infrared light, like what the James Webb Space Telescope sees, right? They will choose colors for that invisible light. For the James Webb Space Telescope, the convention is to assign the color red to the lowest energy infrared light of that image. Right? So when you see the color red in these images, that's not how it would look in real life. That light to our eyes would be invisible. We wouldn't be able to see it at all. But then if you were to see actual red in that nebula, that color has been assigned to a different color. And typically they'll assign it to a shorter wavelength, higher energy color, right? And that's how these images are created. So in the end, the Carina Nebula would not look the way it looks in the images that you see, right? If you were to fly your spaceship alongside of it, it would not look like this. The colors here are not real, the colors are false, but the science behind the colors is not false. And this image is not a fake. This is a real object 7,600 light years away from us. Using false color allows astronomers to enhance the features of our universe that we otherwise wouldn't be able to see, these features that would be invisible to us. So in my humble opinion, I think it's important to know how images like these are produced. So this is something that matters a lot to me. I hope that it will matter to you as well. So thank you very much.